All right, so in our last example, we looked at the line integral of a vector field around a square, and we noted that we could break it up as 4 different line integrals and work it out directly, but we chose to use Green's theorem, and life was pretty good. So in this example, I want us to go ahead and work out this problem the direct way, where we're going to parameterize and then plug in, and then using Green's theorem. So we'll do it both ways. But I want you to get into the habit of doing 2 things before you dive into these problems. I want you to get into the habit of checking whether or not your vector field is conservative. Because if it is, that's a big game changer. You really want to know that. So let's just go ahead and realize that this is going to be my P, and this is going to be my Q. And to check if I'm conservative or not, let's just say, let me zoom in a little bit here, sorry. So let's say, is F conservative? And so we'll do our test, and so we're just going to compute P partial Y, and we get, what, -4. And then we're going to compute Q partial X, and we get, what, 3x squared. And so you can see these are not, sorry, I said P partial Y, that's -4x. I don't know why I dropped the x. P partial Y is -4x, Q partial X is 3x squared. And so it's clear that these are not the same. So we'll just put a not equals there, and so we can say a big no, F is not conservative. And that shouldn't surprise you in some sense. If it is conservative, then the answer in this case is 0, because you know that C is a closed curve. I don't even have to graph C to know that C is a simple closed curve, because the little circle there tells me it is. However, the other thing that I want you to get in the habit of doing is sketching a picture of your curve before you dive in. I saw a few of you on our exam 3, where some of the double integrals, you didn't sketch the region, and you would make some mistakes. And so a picture really does help us keep things straight. We still might make mistakes, but certainly helps. So get a picture down of the region we're going to work over. This is my curve C. I'm going to think about C as having 3 pieces. The quadratic, we'll call that C1. The horizontal, we'll call that C2. And then the vertical, we'll call that C3. And so we're going to parameterize each piece and work it out directly. So before we dive in, I like to go slowly in these problems and write a lot, so that if I come back and read this later, or if someone else, maybe a student of mine or a friend or somebody, wants to read my work, then hopefully it makes sense to them. So I'm going to go ahead and show what I'm doing. I'm going to break up the line integral over the whole curve C as the integral over each piece. So I'm going to not write a circle on this line integral. Maybe you should tell me why. Pause the video and ask, why did Dr. Klein leave this circle off? Well, the answer is the circle only goes when the curve is simple and closed with positive orientation, and C1 is not closed. So I don't put a circle there anymore. Oops, tiny thing, but it certainly matters. Plus integral C2 f dot dr plus integral C3 f dot dr. So that's the strategy, and now we want to work out this problem over each one of these curves. So let me charge my Apple Pencil here for just a moment, and then we'll keep going. So let's think about C1 together. How does one parameterize C1? Maybe you should think about that while I charge my pencil up. Hopefully it's got enough juice to roll here. So for C1, C1 is given to me by, let's just go ahead and make a section for this. So on C1 is given to me by y equals x squared. And so my parameterization in this case, when you have y as a function of x, your r of t is going to be x is t, and then y is f of t, which is just going to be t squared. That's one way that you can always do that. We want to think carefully about our t. T is going to go from 0 to 1, and that's going to take you right along that curve. So we've parameterized C1 without too much difficulty. We know we're going to want r prime of t, so we'll go ahead and compute that. We get 1 and 2t. And so now we're interested in this integral. So we're going to pop that right there. And then let's work it out. So I've lost track of what f is at this point. So let me go up, and we'll just copy it and pop it down here. let's just paste it right there, and let's make it bright pink so that we know to erase it later. Okay, so there's my f. I'm going to plug my parameterization r of t into f. Everywhere I see an x, I put a t. Everywhere I see a y, I put a t squared. And so this becomes the integral from 0 to 1. Let me scoot this down ever so slightly. Integral 0 to 1 of what are we going to get? Well, we're going to get x is going to be a t, so I'm going to get a, t squared. And then I'm going to get minus 4t cubed. All right. And then I'm going to get, on the next one, I'm going to get a t cubed minus 2t squared. And so that's that. Then I'm going to dot this guy with r prime. And r prime we got was 1 comma 2t dt. And so I will go ahead and take the dot product, combine like terms, and you should end up with, well, let's just work it out together here, actually. So if we take the dot product, we're going to get, let's see, integral 0 to 1. We're going to get a t squared minus 4t cubed. That's times 1, add. And then we're going to get a plus 2t to the 4th minus 4t cubed. And so dt, so I get the integral from 0 to 1 of minus 8t cubed plus 2t to the 4th, and then I get a plus a t squared dt. And I will let you work that one out, and you'll just get negative 19/5. That's just a Calc 1 problem. You can handle that. Let's go on now and look at the next curve. We want to work on C2. So I want to keep moving along here so this video doesn't become too terribly long. So we're working on C2. We're on this part of the curve. We're just on a straight line, and we're going from the point 1, 1 to the point 0, 1. So we should say that. We're going from the point 1, 1 to the point 0, 1. And there's different ways to parameterize this curve, but the way that I like to do it is the way that we've always done it, and that's where you just say head minus tail. So I want my direction vector v, and my direction vector v is going to be 0, 1. I'm going to think of that as a vector, subtract 1, 1, and I'm going to get the vector, minus 1, 0. So there's no change in the y direction. That makes perfect sense, right? Y is horizontal, and we are going negative 1 in the x direction. So very good. So now we can write down our r of t. It's our starting point as a vector. We're starting at 1, 1. And then we're just going to go t times our direction vector v, which is negative 1, 0. So this becomes 1 minus t, comma 1. And that certainly seems to do the job. We are typically going to have t between 0 and 1. Let's check, though. When I plug in 0, I'm sitting where I want to be at 1, 1. That works. And when I plug in 1, I'm sitting at x is 0, y is 1. That works as well. So we've successfully parameterized our curve. And so now we can set this thing up. And so the integral along C2 of f dot dr, I need to go up and copy my pink f and just drag it along here so I can see what f is. Oops, I don't want to copy it. I want to cut that. We don't want that there anymore. So we'll cut that out, and we'll just pop this down here out of the way. Okay, there it is. Now I can see to plug in my parameterization. So everywhere I see an x, I'm going to get a 1 minus t. Everywhere I see a y, I'm going to get a 1. So this is going to be the integral from 0 to 1 of a 1 minus t squared minus 4 times 1 minus t times 1, comma, I need my vector here, comma, 1 minus t cubed minus 2. And then I'm going to go ahead and multiply with the dot product here. So let's see, dot product of the derivative, r prime in this case is negative 1, 0. I like the 0 a lot because that actually wipes out this whole term. And so this just becomes the integral from 0 to 1 of, let's see, we're going to get a negative 1 minus t squared plus 4 times 1 minus t dt. And again, you can work this out. Just to expand out this polynomial if you want to, whatever you're going to work it out and you should come up with 5/3 for that one. So that's that on C2. Let's keep rolling right along here so that we don't spend forever on this. So let's look at C3. Where are we going? Let's go back up to our picture. We're going from this point down to the origin. So we'll scroll back down. Apologies if I'm making you seasick. We're going from x is 0, y is 1 to x is 0, y is 0. And so my parameterization r of t is going to be my starting point 0, 1 plus t times head minus tail, so 0 and then negative 1 again. And so this guy becomes what? 0. X is always 0, and then y is 1 minus t. And we want our t's between 0 and 1. There are other ways to do this, but this way seems to work well for students. Check when you plug in 0, you're sitting at 0, 1. That's where we want to be. When I plug in 1, I'm sitting at 0, 0. So that works. And so now let's paste our pink F so that we can keep track of everything. And now we can write down the integral along C3 of f dot dr is the integral from 0 to 1. Okay, so I'm plugging in 0 for x, so that's nice. So I get, 0 minus 0, that's all 0. And then 0 cubed minus 2 times y is a 1 minus t. Then I'm going to dot with the derivative, so I'm just going to dot with negative 1. Oops, it's r prime is a vector, so it's going to be 0, negative 1 dt. And so I get the integral 0 to 1. Okay, let's think it through. 0 and 0, that gives me 0. And then this one, I'm going to have negative 1 dot this guy. So it's just going to be 2 times 1 minus t dt. So this is just the integral 0 to 1 of 2 minus 2t dt. I'll let you work this one out, but you should get 1. So you're actually going to get just a 1 there. And so the point is, let's actually finish the problem. The point is the line integral over c of f dot dr is add them up. So C1, we got negative 19 fifteenths, negative 19 fifths. C2, we got minus, let's see here. I have it written as a 5/3. You know what? I got it wrong. It's actually a negative 5/3. Apologies for that. Some of you were probably wondering what on earth was going on. I dropped a negative. So this, on C2, you should get negative 5/3. There we go. So this is negative 9 fifths minus 5/3, and then we're going to get a plus 1, which is a 7 fifths. So the whole thing, when you work it out this way, you get 7 fifths. Even though this video has gone on longer than I would have liked, let's go ahead and do Green's theorem just to keep it contained into one video. So, oh my goodness, what does Green's theorem say? Let's just say Green's theorem, and then I think you'll be amazed how much faster it is. The line integral over c of f dot dr is the double integral over my region D inside of q partial x minus p partial y dA. Let's set up the double integral first. So we'll scroll up to our picture, and we can see, let's cut this thing with respect to y. So y is going to go from x squared to 1. X is going to go from 0 to 1. Y goes from x squared to y equals 1. X goes from 0 out to 1. So scroll down. Let's nail the bounds. Y goes from x squared to 1. X goes from 0 over to 1. And then q partial x is going to be, what, 3x squared. And then minus p partial y, you're going to get a minus 4x is a plus 4x, and we're going to do this dy dx. I'm not going to actually evaluate this with you just for time's sake, but please pause the video, work it out. You know what you're going to get. You're going to get 7 fifths. And so even though we might not like setting up double integrals, at this point the double integral was really straightforward. The bounds were clean, and the integrand is super nice. There's really not much to this problem using Green's theorem, whereas it took a lot of work. It took a full page of, actually more than a page of scratch work here to work it out directly. So Green's theorem is definitely your friend. You want to learn it and be able to use it, And in the next video, we're going to discuss some other ways we can use it.